Hello students, we'll start with next topic, that is Hilbert's curve. We'll directly see the image so that you'll understand better. You can refer the notes uploaded on Google Classroom for better vision. Okay, so let's start with Hilbert's curve. Hilbert's curve is also called as piano curve. So better you know the other alternate option, as it may in exam you know what name they will ask. So Hilbert's curve or piano curve. Hilbert's curve is very simpler and can be implemented easily. It basically deals with the concept of squares. So, and the curve actually begins with square. So the generation of curve here requires approximations one after the another. Now in the first approximation, what we do is to divide the square into 4 quadrants, like you can see in figure A, and then draw the curve which connects the center points of each quadrant. As we can see in the figure A, we are dividing the square into 4 quadrants, right? And after that we are drawing the curve and connecting the center points of each square. Then this is first approximation. Now for a second approximation, the second approximation will be to further subdivide each of these 4 quadrants which we can see in figure A, and draw the curve which connects the center point of each of these finer subdivisions. Did you get it? In figure A we have 4 quadrants, and taking the center point of each quadrant we draw the curve. Now in second approximation we are subdividing these 4 quadrants into further 4 quadrants, and then connecting each of the center points and drawing the curve. Now the third approximation again. Now what happens in third approximation? Here again we'll subdivide each quadrant and continue the process, that is to connect the centers of each square. Now when we look at the curve, we'll know that the curve is not getting overlap at any point, right? Curve is arbitrarily close to every point in the square, and we know that there is no limit to this subdivision. So the curve fills the square. Ideally, the length of the curve is infinite. With each subdivision, the length increases by factor 4. Since the curve is equivalent to line only, its topological dimensions must be equal to 1. Did you get it? Since the curve is equivalent to line, for line we have already seen that the dt, right, topological dimension must be equal to 1. If you remember, we have already seen this in fractals for curve generations. Revise once, see that video or refer your book, and you will get that the topological dimensions we have seen. For line it has to be 1, and for plane it has to be 2, and whenever we think of a 3D object, the dimensions has to be 3. So dt equal to 1 for line, dt equals to 2 for plane, and dt equals to 3 for any cube, sphere, or any, we can say, a 3D object, right? So here, as it is equivalent to line, the dt should be 1. Now at each subdivision the scale changes by 2, that is at every approximation we are dividing plane into 4 quadrants, right? But the length of the curve changes by 4. Now at each subdivision, so we need 4 scaled curves to form original curve, right? We need 4 scaled curves to form the original curve, and this is what we get here. That is n equals to s to the power d of f. Therefore now here n is 4 scaled curves So at the end we can get d of f equals to 2. So we can say that Hilbert's curve has topological dimension 1, right? That we have seen because it's a line, and fractal dimensions equal to 2, as we found out here. Fractal dimension 2. So we can say that it is line only, but it is so folded that it looks like a 2D object. So Hilbert curve is a line, but it is folded in such a way that it looks like a 2D object. This is Hilbert curve. Let's revise once. Hilbert curve, also called as piano curves. Here the process is continuous successive approximations we do. First approximation is to divide the square into 4 quadrants and then connect all the centers of the square and draw a curve. Second approximation, further subdivide the quadrants into further squares and again connect the centers of each square. Then go on subdividing in such a way, and then there is no limit for subdivision. You can go on dividing here, as if the topological dimension must be always equal to 1, so it's d of t is equal to 1, as the curve is equivalent to a line, so the topological dimension is 1. Then fractal dimension we found out to be 2. So here topological dimension 1, fractal dimension 2, and we can say that Hilbert's curve is a line, but it is folded in such a way that it looks like a 2D object. Okay, that's it. So and next we'll see triadic couch curve.